Assalamu alaikum students. Welcome to our new lecture on hydraulics and irrigation engineering for this semester. We looked at different things in the previous week related to reservoirs and to dams. And inshallah today we are going to finish this topic, the topic related with reservoir and dams, and we will move on to sediment and sediment control, sediment properties and those sort of things. But before we move on to that, we have to do certain numericals, and then inshallah we'll finish with the reservoir related section of your course content. So these were the things that we said that we will be covering. In the previous week we looked at the selection of hydropower sites, then we moved on to the components and layout of hydropower schemes, followed by the types of storage dams and then forces on dams, and briefly we touched upon design of gravity dams. Today inshallah we'll do numerical on that in Excel for calculating forces on dams. We'll be considering but a relatively easier problem, and then we'll move on to more complicated problems. But before we move to the numerical problems, we have to do operation and regulation of storage reservoirs, because this is the part that we are still left to do. So operation and regulation of storage reservoirs, we'll start with that, followed by the numerical, and then next week we'll be discussing sediment transport in channels, sediment problems in reservoirs. Or maybe I'll be uploading another lecture as well to finish this thing off quickly, because we still have a couple of other things to cover before your final term exams. Anyways, we looked at reservoir types in the previous lecture. You remember that, and hopefully you would have also read your books and other sources to augment your knowledge. You would have observed that we have usually uneven flow in our rivers. Generally we have higher flows in summer and low flows in winter, and this is because in summers we have more glacial melt, and that melt is then contributing to the total river flow. So we have higher volume of water coming in summers than in winters. But if we look at the demand of water, you would see that because in our country, in Pakistan, we have two major cropping periods, the Rabi and Kharif period, and we always need water. So demand is always there, availability is uneven, and we have to cater for that. And we cater for this thing by regulating the stream flow. We regulate the stream flow in a sense that we provide certain storage reservoirs, and then we try to collect that water which is surplus in summers, and then we use it in winters when the demand is there but inflows are less, so we use that water then in winter. And this is basically a simple curve of storage reservoir, where we see the two kind of curves. You see this blue curve which signifies or which shows the supply part, the red one is the demand part. So you see that with respect to time, I mean if x-axis is our time and the y-axis is either supply or demand, then you would see that with time there are times when we have higher supplies, and then there are times when the supply diminishes or it is less than the previous periods. Initially we have demands. The demands are, in some months the demand is low, and it's understandably, I mean if this is, let's say, if the x-axis show us the months, this is January, February, March till December, then it's understandable that in winters we have relatively less use than in summers. So in winter months the demand is comparatively lower, and as we move to the summer months the demand increases. Fine. So you have these two curves with which intersect each other at a particular time. And basically, if you look at it, this is that part where you have more demand than the supply available, and this is that amount which we need to store. If somehow we can store this amount of water in this period, then when this period comes up and when we have higher demands, then we can meet that demand by the water that we have stored earlier. If we with time, if we take the difference between these two curves, then obviously we'll get a curve something which is like this, and the highest value of that would be the amount of water that would be needed in a reservoir. And we know that reservoirs are usually constructed for multiple purposes. We do not create a very big reservoir or a reservoir which is very expensive to be built for just one purpose. We make a reservoir and we make sure that that reservoir is used for multiple purposes. Those purposes can be irrigation, sediment control, and then in a lot of countries transportation is also done through rivers. The big ships that are moving in rivers and they are transporting different materials from one city to another by transporting them through the river canals. We also generate electricity for them and all different kind of uses. So the uses are sometimes conflicting. You see, if you are using a reservoir at the same time for two different purposes, let's say the flood control and then irrigation, these two are sometimes conflicting uses. For flood control, you would ensure that your reservoir has maximum space in it, so that if a flood is coming up, you have enough space in your reservoir to store that water. Fine. On the other hand, for irrigation, you always need, or for power supply, you always need your dam to be filled with water, so that you have maximum head available and you can generate maximum electricity out of it. So you see, we have two different uses, the irrigation or power generation and also flood control, and these are in conflict with each other, and we have to keep these things in mind, that we have to meet each and every demand and we have to use the reservoir up to optimum level in most useful way. So sometimes it's not very easy, and we'll see at the last part of this lecture we'll be looking at different rules or different operation rules of reservoir, and you'll see how we maintain or we try to achieve both the targets or both the objectives by regulating the flow in the reservoir. We looked at the storage and distribution reservoirs, and we said that we can control those the outflow from those reservoirs either through weirs or through gates, and related to both of them we looked at the hydrograph, how the hydrograph would be changed if we are installing gates or if we are controlling water with the weir. The main thing, if you remember, was that we are reducing the peak and also we are trying to delay the peak that is coming in the hydrograph. Anyways, if we are making big reservoirs, we have to also consider that with each dam or with each project we are going to face a lot of environmental problems as well. If we look at the Basha Dam that is currently under construction, initial estimates say that almost 35,000 people would be moved from their ancestral places, and they have to go to other places. So they have to leave their homes where they have lived for maybe hundreds of years, and they have to move from that place to some other place, some new places. A lot of very expensive land that they own that would be submerged, because you see Basha Dam is not in the plain areas where you have a lot of area available to you. It's a mountainous region, and each acre or each hectare of an area really matters to them. And a lot of if 1500 acres of agriculture land in the mountains region, it's quite expensive there. So that would be submerged, and also then a lot of kilometers of Karakoram highway have to be readjusted. Some part of it would be flooded. A lot of things are involved when we are planning for big reservoirs, and the main aim for us is to achieve this head. So let's see, if this is a river which is flowing in a mountainous region, and if we are making some reservoir up here, so basically this is the total head that we are aiming for. Somehow we'll create a blocking structure here, we store water, and then maybe we are making our hydropower station somewhere here, so that we have this head available to us, and then we can make enough electricity out of it. And the main thing when we are planning our reservoirs in mountainous region is that we are trying to make a reservoir which is more in depth and less in terms of its surface area, so that we can minimize the evaporation losses. You see, for example, let's say this is a reservoir, and this is a plane view. We are looking at a reservoir from above. If this area is minimum, then obviously the evaporation from this area would also be minimum. So what we are aiming for is this depth, so that we can store water with the depth. The depth is more as compared to the area, so that we can minimize the evaporation losses. You see, we also have kind of relationship here. You have for a particular area. For example, this A1, let's assume that A shows the area and H shows the height, or let's say the depth of water in a reservoir. So with every depth there is a certain area associated with it, and we will say that, okay, if my reservoir has a height of, let's say, 1000 feet, then with 1000 feet the area associated, or the surface area of that reservoir would then be something like, let's say, 1500 square kilometer, for example. So we have a relationship in a reservoir between the height and the area. And this relationship is very important, because this is what ultimately we would be using for the operation rules of reservoir, which is coming up in the next few slides. And what we have to ensure is that the yield of the reservoir is always met, and yield is usually defined as the amount of water which is delivered from a reservoir to meet all the downstream requirements. So every reservoir would be having a particular yield based on the incoming water or incoming flows and the demand of that area. We already have looked at these basic definitions, where we said that we should have a sufficient impervious and sound formation of bed, so that we can have an ideal reservoir, and also deep and narrow valley, so that we can minimize the evaporation losses, and also the low cost of the reservoir that is being made in a certain area. And the main two things that we want to look at today is the elevation area curve and elevation storage curves that we usually get, and we try to use them. So again, refer to the previous picture where we said that with each height of the dam there is a certain area associated. Once we have a reservoir, we create this kind of a relationship. Ultimately you would be having this kind of relationship, where just by looking at the water in the reservoir you would find out what the area is, or what the surface area of your reservoir is. So on x-axis you have area, on y-axis you have the elevation of the dam. Similarly, another relationship which is also associated with the elevation is the elevation storage curve, or elevation storage relationship of a particular reservoir. And here we associate the height or depth of water with the storage that is there in that reservoir. So area is obviously in square meters, storage would be then in cubic meters, and then we can have a relationship between them. So let's say if you have a particular area, and that area is between, for example, let's say we are trying to find out the volume that would be between these two lines, or between area 1 and area 2. We look at the heights here, h1 and h2, we take the average of it, and we multiply the height with the area to get the volume. Fine. So ultimately we have these two kind of relationship where we associate the storage and the area with the depth of water, so that ultimately we can operate our reservoir. Understandably, if we draw the two curves here on the same axis or in the same graph, your primary x-axis contains volume, for example, and this volume is increasing in this direction. So volume here is less and volume here is higher. Similarly, area is on the secondary x-axis here, and it is increasing in this direction, telling us that the area here is less and area here is more. And then we have these two curves. This one is for the area versus the elevation, and this is for the volume versus elevation. You have just one primary y-axis which shows the elevation in meters, and also we have these lines, these horizontal lines, which shows different parts of reservoir. Sometimes we have to divide our reservoir into different zones. We have a zero pool, we have minimum operation level, or this is usually the level where you have the lowest intake structure in the reservoir. Then you have a spillway crest, and then the operation level. Anyways, if we look at this graph, you see, let us first look at the volume line, which is this one, and we see that with increase in elevation, if I look at the volume curve, then my volume would be increasing, and this is understandably so. And similarly, if I look at the area curve, then also with increase in area, I see that with increase in elevation, I have also higher areas in my reservoir. And these two curves would always be used in conjunction to find out what should be the outflow from my reservoir. If I know that, okay, this is the depth of water available for me in a certain reservoir, then I can calculate the total volume available with me in that reservoir, and based on that I can then regulate the flow so that I can meet the demand. If my volume is less, then I would say that, okay, even if demand is higher, but I have to keep the future need in consideration, and I'll regulate my outflow from the reservoir, keeping in mind where my water is, whether it is in minimum operation level or whether the water is somewhere near the spillway crest. And the zones that we were talking about, so usually what we do is that if this is my reservoir, I'll divide my reservoir into different zones. Of course, there would be some dead storage here where the sedimentation is taking place, then minimum pool level, or let's say in the previous minimum operation level. These two names can be used interchangeably, and this is the level where your lowest intake structure usually is. Sometimes we have intake structures at different levels, and the one which is on lowest level is one where your minimum operation level, or where your reservoir can be operated upon. Then you have always a certain portion which you allocate for the flood control, and also some other uses. And based on that, we decide about how to operate my reservoir. Reservoirs are normally operated through operation rules. We have defined operation rules, and these operation rules are available with the plant managers, plant operators. They always have these rules in front of them, and they look at the time, at the season, and based on that they try to follow these operation rules. Um, we divide our time into certain periods. For example, let's say a known flood season and then the expected flood season another times, and we try to maintain different levels here. You see, if I'm looking at this storage at the conservation level, if my water is, I have to ensure that the water is somewhere here. When I'm entering the flood season, I have to reduce my storage. I have to draw down from the initial levels, so from point A to point B I have to reduce my levels in the reservoir to this level, so that because there is a flood season expected, and in flood we have higher discharge, so I have to ensure that if this is my maximum storage level, then at least in flood season I have maximum space available with me so that I can store water. And once the flood season is over, then I'll increase my water level to this value, and then I'll operate the rest of the year at this level. And this is a very simple operation rule, where you have different zones and you are trying to maintain or trying to meet the operation rules. Once we develop our operation rules, and let's say if my reservoir is made for different purposes, as we said earlier, multiple objectives of reservoirs, for example the flood and hydropower and irrigation and other needs there, then usually the operation rules also becomes complicated. Let's look at this picture again. This is from January to December for a certain reservoir. This is reservoir water level, and you see we have different kinds of curves here. This one is the firm curve, or that level where you have to ensure so that certain amount of water is in the reservoir and you can meet the demand of, let's say, of hydropower. Then you have different zones available here, and you see that there are with respect to time, you have to ensure that your zone, different zones in the reservoirs have different levels. If this is my dead level, then I ensure that in March I have to have this much of water available to me in this zone 5, and also this much of water if I am in the zone 4, and similarly in other areas. Again, the same drawdown period, and then slowly and gradually I have to increase my water level so that I can refill the water, and then I am at the maximum level that is available there. So reservoir operation rules are usually developed. There are different methods to develop them, different techniques available where you try to optimize your objectives so that different kinds of needs can be met. So this is what it was that we left from the previous week. We'll be discussing about the sediment transport in channels and sediment problems in reservoir in the next week. First we have to look at the loads on the dam that we looked at in the previous week. If you remember, we looked at this picture in the previous week, and we said that a reservoir would be having different kinds of loads on it. We looked at the water load, we looked at the self load of the dam, and we also looked at the water load on the tail side, and we looked at different formulas. The formulas were something like this. If we are calculating the water load, then and we'll see today how to calculate it. This was the formula for it, where we use the unit weight of water into height of the water, and this is the load at the bottom of the reservoir. And then usually we have a triangular kind of shape of the water pressure, which is minimum on top and maximum at the bottom, so we have a triangular shape. We'll be looking at this now and it would be clear. And at the bottom the maximum pressure is there, gamma of water into the height of water, and then we calculate the area of that triangle region, and we calculate the total load on it. So water load there, and then the self load was also looked upon, where we just take the unit weight of concrete, multiply it with the area that dam is occupying, multiply them, and we get the primary loads. So let's look at one problem that we are going to solve. Now this is one typical problem, a very simplified problem that we have to solve. You see, we have a gravity dam. Gravity dam is usually a concrete dam, and we have to calculate the maximum vertical stresses at the heel and toe of the dam. If you remember, we said that this part is called the heel of the dam and this one is the toe of the dam. The unit weight of concrete is given, which is 23.5 kilonewton per cubic meter. We have to calculate all the loads on the unit length of the dam. The allowable stress in concrete is also given, which is 2500 kilonewton per square meter, and also the unit weight of water, which is known to you, is 9.81 kilonewton per cubic meter. As I said earlier, this is a simplified problem, and why I mean by simple problem is that we are going to ignore the earthquake loads here, and we are also going to ignore the water pressure loads, the pore water pressure load, which is usually occurring in this direction from in the vertical direction from the bottom up towards the dam structure. So we are going to ignore it for the time being. We'll do it in other numericals. In this problem, we are just going to calculate the load due to water on upstream side, load of water on the downstream side, and then the self load of the dam. Fine. I've started this solution of this numerical here, and we'll complete it together. Just first look at the structure of the dam. We have a very simple structure, a triangular structure. Different reduce levels are given. At the bottom, the reduce level is 205 meters. At the top, or let's say the maximum water level, has 285 meters, which means that the water stored in the reservoir is 285 minus 205, which comes up to 80 meters. Fine. The total height of the dam can be calculated, because at the bottom it is 205. The maximum level here is 289, so 289 minus 205 would give you the maximum height of the dam structure. Then you have this inclined surface, the slope of which is also given to you, 2 by 3, or for every 3 steps in vertical direction, we are moving 2 steps in the horizontal direction. The water level on the downstream side is also given. The reduced level of water is given also there, 211, and we are going to calculate the loads, all the loads except the earthquake and except the pore water pressure. So let us do this problem. Now, first of all, I am considering the self load of the dam, and by self load of the dam I'll mean what is the total weight of this structure itself. You see, we have to calculate the load of this dam. Again, remember that although it's not required in this numerical, but we are also going to calculate the moment arm of all these forces, and we are going to calculate the moment arm about the toe of the dam. This is, as I said earlier, this is heel of the dam. This point is called heel of the dam. This one is called the toe of the dam, and we are going to calculate the moment arm of forces around toe of the dam, so that we can find out in which direction this reservoir is turning. Now water is stored on this level, on this side, you see, so there would be a resultant force of water acting in this direction, which will make the reservoir tilt in this direction. If I have water here, this water is exerting pressure on the dam structure in this direction, and it will make the dam tilt in this direction, in anti-clockwise. So the water here is making the dam turn around in clockwise direction. The water on the downstream side is making the dam turn in the anti-clockwise direction. Similarly, if I am looking at the self-weight of the dam, and if I say that this is the center of gravity of all the load, then this would be turning again the dam in the anti-clockwise direction. But if I'm calculating everything about the toe of the dam, fine. We've also been given the center line of drainage gallery here. For the time being, just ignore it. We will use the drainage gallery, or why it is used, for what purpose it is used. We'll be doing it maybe in the next classes. But this is usually that point where your pore water pressure line is breaking. And what I mean by breaking is that there is discontinuity in the pore water pressure at this line, but because we are not calculating the pore water pressure, so you can safely ignore that. So let us first of all calculate the self load of the dam. You see, if I am looking at this structure, then I can very easily divide this structure into two sections. One would be this rectangular. If I draw a straight line from this line towards the bottom, then I have this rectangular shape. So one is this shape, another is then this triangle. If I calculate the area of these two parts, the rectangular part and the triangular part, and multiply it with the unit weight of water, unit weight of concrete, which is given to me, 23.5 kilonewton per cubic meter, then I can calculate the self load of the dam. This self load of the dam is acting vertically downwards, and we will also calculate the moment arm of both the shapes, the rectangular shape and the triangular shape. So first of all, let us look at the rectangular cross section. If I am calculating the area, then you see the total height is 289, reduced level is 289. Here at the bed the reduced level 205, so 289 minus 205 would give me 84 meters. So the height of this rectangular section is 84. 6 meter is the width of it, and I have to calculate it for 1 meter per meter of per unit meter of width. So the area would come up to be 6 multiplied by 84, and this would be equal to 504 square meters. Fine. If I have this area and I know what is the unit weight of concrete, 23.5, I multiply 23.5 with this total area, and I'll get the force in kilonewtons, 11,844. Now let us look at the lever arm of the rectangular section. You see, I have this 6 meters of width of this rectangular section, the midpoint of which would be at 3 meters. Fine. The total width at the bottom is 56 meters. So 56 minus 6 would come up to be 50, and then I have to move 3 meters so that I can reach the midpoint of this rectangular section. So I have 53 meter of the lever arm of this rectangular section. So lever arm of rectangular section is equal to 53. As you can see in the formula, 6 divided by 2 plus 50 would give me this 53. And then if I am calculating the moment, the total moment generated by this rectangular section, I just have to multiply these two values. This 11844 multiplied by 53, and I'll get 627,732 kilonewtons per meter, and this is in anti-clockwise direction. You see, this would be in this direction, anti-clockwise, and I'm assuming, or I'm taking anti-clockwise as positive moment. Fine. This is for just this small rectangular part of the dam. Now just let us look at this triangular part and let us calculate this thing here. First I'll calculate the area. Now what should be the area of that? The base of this is now known to you. This is total is 56. 56 minus 6 is 50. So this would be the base is 50 meters. So it's equal to 50 multiplied by the height. Now the height is given here. This slanting section is starting at 280 reduced level. This is 205. So 280 minus 205 would give me 75. The total height is 75. So 50 multiplied by 75 multiplied by 1 by 2 or 0.5. Fine. This is the total area. 1 by 2 base into perpendicular, simple, and I'll get the total area. This area is in square meters. Fine. Next is to calculate the force out of it, and I just have to multiply the area with the unit weight of concrete and multiply it with 1, because I'm calculating it for the unit width of the dam. So it's equal to this value multiplied by the unit weight of concrete and then multiply by 1, and I'll get this value of 44062.5 kilonewtons. Next is to calculate the lever arm of the triangular section. And what should this value be equal to? This is a triangle with a width of 50 meters. We know that the center of gravity, or the forces acting on a triangular section, are 1/3 or at the base value. So we will get 1 by 3 into 50. Fine. So this is equal to 1 divided by 3 multiplied by 50. So this is acting at 16.66 meters at this point. From this line, 16.6 meters here. But I have to calculate it from the toe. So I have to minus it from 50, because the total width is 50. 50 minus this value would give me now the, so I'm simply putting two brackets here. I'm 50 minus this value, and this would give me the lever arm in meters. To calculate the moment about the toe of the dam, I just have to simply multiply these two values. is equal to this multiplied by this value, and I'll get the moment generated by the self load of this end of this triangular section. Again, this is anti-clockwise, and I'm assuming that anti-clockwise is positive, so this is what we are getting. So this is now the self load of the dam. This is the self load of the dam which is acting in the downward direction. We divided it into two parts, the rectangular part, the triangular part. We calculated the area of the two parts and multiplied the area with the unit weight of concrete which is given to us. And then we found out the center point of the two shapes, and we calculated the distance from the toe, and we calculated then the moment off of it. It's very simple, very easy. I'll be sending you this Excel sheet so then you can look into it and do the things yourself. So this is just the self weight of the dam. Now let us also calculate now the water pressure. Again, the water pressure on the upstream side and the water pressure on the downstream side of the dam. You see, water here is stored at a particular water level, which is equal to 285 minus 205. Okay, let me just write it here. We have to calculate the water weight on the upstream side and also on the downstream side. So first we are looking at the upstream phase. Now, as we said, the water level is 285 minus 205, which would be 80 meters. Now this water is stored on the upstream side. I have minimum water pressure at the top and maximum at the bottom, so the line would be something like this. At the bottom, the maximum pressure would be, as we said in previously, gamma of water into this height. Fine. So let us calculate this thing. Maximum water load at the bottom is equal to, this is unit weight of water multiplied by the height of water. The height of water is 80 meters. Fine. So this is now the value, the base value. If you got the base value here, 784.8. Here it is 0 at the top. I've got the base value, I've got the height. If I calculate the total area, this would be the total pressure of water on this vertical wall of the dam. Fine. So I'll just calculate now the area of a triangle, because it's in a triangular shape. So this would be equal to 1 divided by 2 multiplied by the base. Base is this value multiplied by the height, which is 80, and this would give us the value of water pressure in kilonewtons. Again, moment arm of water, what would be this value equal to? If this is a triangle, then it would the center line would be acting here 1/3 from the base. So this is 80, the total height is 80, and this would be equal to 1 divided by 3 multiplied by 80. So this is in meters, and if I'm now calculating the moment about the toe, So I have to multiply these two values, this multiplied by this, and I'll get a value in kilonewtons meter. Fine. Very simple water pressure on the upstream side. Now let us calculate also the water pressure on the downstream side, and then we are almost done with the question. So just copying the things here. This is now water weight on the downstream phase. Again, we have to delete this because we are going to calculate it anyways. Okay, maximum water load at the bottom. So now water level on the bottom is how much? 211 is the water level on the downstream side. The base level is 205. 211 minus 205 would give you 6 meters. So the tailwater has depth of 6 meters. Fine. So now this load is acting in this direction. First of all, we have to calculate the base value, which would be gamma of water into height. Gamma of water is the same, 9.8, so multiplied by 6 meters. So is equal to, again I'll go scroll up, this value multiplied by 6. Fine. Now if I'm calculating again, this would be in a triangular shape. I have to calculate the area of it. Again, 1 divided by 2 multiplied by this value multiplied by 6. 6 is the height of water on the downstream side, and I'll get 176.58 kilonewtons. Again, the moment arm of this water here, which is stored here, again it's a triangular shape. 1/3 of 6 meters should be the center point where the total load of water on the downstream side is acting on this dam structure. So this would be equal to 1/3 of 6 meters, should be coming up as 2 meters. I'll multiply these two values to get the moment arm, or the total moment generated by the tailwater on the dam side. Now these are all the forces. We have the self weight of the dam, and then we have the horizontal forces on the dam acting on the upstream side and on the downstream side. If I am calculating the resultant horizontal forces, so what would be resultant horizontal force equal to? Very simply, because horizontal forces, you see, horizontal forces are acting due to water. Self weight is acting in the downward direction, so this is vertical load. We are not looking at it, we are looking at horizontal forces. Horizontal forces are due to water in this direction because of the upstream water, and in this direction because of the downstream water. We calculated both of these forces, so we'll just, and the directions are reverse to each other because upstream and downstream water. So on the upstream we have total load equal to this value. This is positive because it's in the direction of, and it's up to you which value you take, positive, which one negative, but because they are in reverse direction to each other, so we have to take one positive and another negative. So this value minus this value would give me the resultant horizontal forces. kilonewtons. If I'm calculating the resultant vertical forces now, resultant vertical forces, then very simply I have to calculate these two. The self loads are both the vertical forces, 11,844 kilonewtons and 44,062.5 kilonewtons, and both of them are acting in the downward direction, so I simply have to add them up. This plus this is the total vertical forces. So we simply calculated the two kind of forces here, the vertical and horizontal. You see, we earlier said that we are neglecting the earthquake loads. Earthquake loads are horizontal loads. So if we had calculated earthquake loads, we would have included that in the resultant horizontal force. Another force that we neglected, and which we will calculating in some other numericals, is the pore water pressure, which is occurring on the bottom of the dam. And because this is also in vertical direction but acting from bottom to the top, that would be in reverse direction to the self load of the dam. So then we would have also needed to include that in the resultant vertical forces. The self load would be in downward direction, the pore water pressure in upward direction, and then we would have got the resultant vertical forces. This is the diagram that ultimately you will get. These are the things that I already calculated in front of you, 784.8 value, which is here, and all the other values. You look into it. I'll also be uploading them on the LMS, this Excel sheet, and also the solution to it. In this solution, the pore water pressure is also calculated. You should go through it, you should read it. All the formulas are also given in the presentation, in the slides, but we will do it in some other numerical at other time, and inshallah then it would be clear. So till that time, take care and look at the things that we did today, and inshallah we'll be meeting again in few days time. Assalamu alaikum wa rahmatullahi wa barakatuh.